All right, so to finish up this problem, we were testing to see if this third one converged. So we're doing the integral test. At this point, I would say I'm going to integrate 1 over u, which is keep this limit as a approaches infinity. The antiderivative of 1 over u is the natural log of u, but I'll go ahead and plug in with the natural log, or what u was, which was natural log of n. And we're going to evaluate that from 2 to a. That's why I don't plug or change my limits of integration. I usually go back in terms of n. So here I'm trying to see if this limit exists. So this would be equal to the limit as a approaches infinity of the natural log of a minus the natural log of 2. This part right here, the limit as a approaches infinity, that would be infinity. And the limit of natural log at infinity is also infinity. So that means this integral diverges. It doesn't add up to something. It keeps getting bigger and bigger and bigger, which means the series acts the same way. It will also diverge. And it diverges by the integral test. So the answer would just be D. Only those first two converge. All right, looking at this next one. It says, which of the following statements is true? Okay, as soon as I see like this with no other like n squareds or exponents or factorial, that looks geometric-ish to me. It looks like I would rewrite this as like 1/2 to the power of n, which is a geometric series, and I know it converges. But let's see what this says. It says diverges by the n-term test. Well, for the n-term test to work, the limit of the sequence part, that has to be not 0 for it to diverge. But this limit as n approaches infinity is 0, so the n-term test is inconclusive. Diverges by comparison with that. Well, this converges, so I can't say something diverges comparing it with something that converges. And then we just talked about that. That was a geometric series that converges. So I'm going to do the limit comparison test with this geometric series. I know the geometric series converges because the R number is less than 1 in absolute value. If I do a comparison test, I can't set up a direct comparison, a term by term. At least I can't really very easily. So I'm going to say it's the limit comparison test. So the limit as n approaches infinity of this term divided by the one before, divided by this one. If that limit is a positive finite number, then we know they act the same. This one would also converge because we're comparing it to a converging series. So I'm going to multiply it by the reciprocal. And that limit, the most powerful term is 3 times 2 to the power of n. The bottom term is 2 to the power of n, so that limit is 3. Since that limit is positive and finite, they act the same way. Like the terms divided by them, like each term by term divided by itself, it's saying these will be about 3 times bigger than these. But if this converges, multiply that converging series by 3, it'll converge as well. So answer is C. Which of the following statements is true about this series? This one, I've got an alternating series. I don't know if I'd compare it with anything. I'm going to compare it with, I'm going to test the alternating series test. That seems like the appropriate thing to do for an alternating series. For an alternating series to converge, 2 things have to happen. The limit of the non-alternating part has to be 0, which it is, because the bottom exponent has the most powerful term, so that's going to be 0 at infinity. And the terms have to be non-increasing. To me, these look like they're non-increasing. I did a derivative test the first time I did this, and I got the derivative was positive when n is 1, but it was negative every time after that, which I think is good enough to say, but I'm just going to kind of wing it here and see if I can compare the next term. Oops. So the n plus 1 term has to be less than or equal to that. Can we say this for sure? So I'm doing an algebraic test here. N plus 1. Okay, this bottom part, if I expanded it out, would be n squared plus 2n plus 1 plus 3. So it would be n squared plus 2n plus 4. Is this helping at all? If I multiply this times this, n cubed plus 2n squared plus 4n, multiply this out, that'd be what? N cubed plus n squared plus 3n plus 3. So I could basically subtract the n cubes from both sides. I could subtract n squared from both sides. I could subtract 3n from both sides. Can I say that's true for every n? Well, if n was 1, no, I can't say that. So the same problem's happening. So 2 is greater than or equal to 3, but anything after n, or anything after 1, if I plugged in n was 2, then it's okay. So 2 squared plus 2 would be, that's embarrassing, 6. So anything after 1 is good. So I plug in 1, I'm thinking, well, does the first term, let me just list them out now. If I just list them out, plug in 1, I get 1 over 1 plus 3, which is 4. If I plugged in 2, the next term of the sequence would be 2 over 2 squared plus be 7. Then plugged in 3, be 3 over 12. Was this 0.25? I don't know what 2 divided by 7 is. Let's get a calculator. 2 divided by 7 is 0.285, but 3 divided by 12 is 0.25. Excuse me, and then start decreasing again. So I need to do some more research here and make sure that it's alternating. After some point, it should be okay. I'm pretty sure the answer is D. I don't know how to compare an alternating series with anything else. So this is embarrassing. I think it's D. Y'all think about it and then maybe write in the comments what you think number 11 is. If I made a mistake and it's obvious, like tell me, or just go with it and don't write anything in the comments, but maybe help each other out. I'm not sure, but I'll think about it more and tell you later. Number 12, which of the following is required in order to apply the integral test? Okay, that's easy. Positive, continuous, and decreasing. So that one's D, I'm pretty sure. Okay, number 13 is kind of tricky. I'm going to tell you 2 ways to do it. Which of the following? For A, so if the terms of the sequence are always greater than 0 for every term, and the next term divided by the one before it is 2/3, that kind of looks like a ratio test, is always 2/3. So the next term, so if the first term was 3, the next one would be 2/3. The next one will be 4/9. It's always 2/3 of the one what was before it. So that idea of the ratio test, that ratio is less than 1, it converges. You could think of it as, it's actually a geometric series, right? Because so it says limit. It's not geometric. It's close to geometric. If I had a geometric series that the R was equal to 2/3, that converges. That means every term is 2/3 of the one before it. This one says, maybe not always, but that ratio is starting to approach 2/3 at infinity. Then it's basically geometric, but not quite. So I know A of n converges. So the way I looked at this was I said a converging series multiplied by a diverging series would diverge. So that's not it. Can't be that. Oh no, I'm in a pretty color. So I'm going to say it's not A. A diverging series divided by a converging series does not converge. A converging series times a diverging series, because that's R number bigger than 1, cannot converge. This last one, this would be like a converging series squared, which is going to converge, divided by a converging series, because it's just 1 over 3 to the n, which is 1 over 3 to the n. That one converges. So I'm going to pick D, but I'm also going to show you the limit if we actually like compared these two. So if we did like the ratio test with all of these, I'm going to say the limit as A approaches infinity of the n plus 1 term So the n plus 1 term would be 3 to the n plus 1 times a to the n plus 1 multiplied or divided by the nth term. So since it's not a fraction, I don't need to like multiply by the reciprocal. So 3 to the n times a to the n. Looking at this limit value, this would be the limit as a approaches infinity of 3 to the n times 3 over 3 to the n times 2/3, because we're looking at limit, right? I'm not going to write that yet. So this would cancel, and this limit is equal to 3 times 2/3, which is 6/3. That limit comparison test, that's a number that's bigger than 1, so it diverges. I said limit comparison test, ratio test. Ratio test bigger than 1, diverges. Okay, we'll do the same thing with B. So I'm going to do the ratio test, the limit as n approaches infinity, absolute value of the n plus 1 term multiplied by, or divided by the nth term, multiplied by the reciprocal of the nth term. Come back, here we go. This would be equal to the limit as n approaches infinity of 2 to the n times 2 over 2 to the n times a to the n over a to the n plus 1. 2 to the n's cancel, and I've got this limit is equal to 2 times 2/3, which is 4/3. That's bigger than 1. Ratio test says that diverges. All right, let's do it again. Limit as n approaches infinity of the n plus 1 term divided by the nth term. This would be equal to the limit as n approaches infinity. I'm just going to keep it a to the n plus 1 over a to the n. I could go and write 2/3 in there if I wanted to. Times 7 over 2 to the power of n times 7 over 2. That cancels. So I've got this limit is equal to 2/3 times 7/2, which is 14/6. That's bigger than 1. It diverges. Okay, last one, the limit as n approaches infinity of the n plus 1 term squared over the n plus 1 multiplied by the nth term reciprocal. Rewrite this. That cancels. So I've got this limit would be 2/3 squared times 1/3, which would be less than 1. So that one converges. All right, number 14. Hopefully we get these multiple choice done in the next couple minutes before class starts. All right, where are we at? 14. All right, that's not multiple choice. All right, if the infinite series blank has n partial sum is that, what's the sum of the series? If it asks you for what's the sum of the series, there's a couple of ways to look at this. The sum of the series, that means this is geometric. That's the only one we know what it adds up to. So back on the first day of Unit 10, we said the limit of the partial sums is equal to this series value. The problem is we usually can't write out an equation that would give us the partial sum, like equation in general terms of n. So this is pretty rare. This would be equal to the limit of this 1/7 minus 1/7. Okay, so as n approaches infinity, that term on the bottom grows up huge, so it blows up. So it's 1 divided by a huge number, which is basically 0. So this would be equal to the limit of 1/6 times 1/7. Look at that. Keeps happening. You're watching this video, hope that makes you happy. Some of y'all rolling your eyes. So the answer is 1/42. The other way to do this is to rewrite this as a geometric series where you can find out what r is. This would be 1/7n times 7, which would be equal to the series starting at 1 going to infinity of 1/7 times 1/7 to the power of n. I can rewrite that as just to the power of n like that. So the r number is 1/7. The series adds up to the first term, so plug in 1. Plug in 1, I'm going to plug in 1 back here just because it looks better. So plugging in 1 for n, it's 1 over 7 squared, so 1 over 49 is the first term, over 1 minus r, which is 1/7. So 1 over 49 divided by 7/7 minus 1/7 would be 6/7, happened again. 1 over 49 times 7/6, divide that by 7 because that reduces, so it'd be 1 over 7 times 6, which is 1 over 42, same thing. For what value of r does the infinite series blank equals this? So the only way a series can add to a number that we know about is geometric series, and it's the first term in the sequence over 1 minus r. That needs to equal 22. Okay, the first term in the sequence I get by plugging in 0. So 0 to the power, sorry, r to the power 0 would be 1. So the first term is 10. So solve this. Multiply both sides by 1 minus r. 10 is equal to 22 times 1 minus r. 10 is equal to 22 minus 22r. Subtract 22, negative 12 is equal to negative 22r. R is equal to 12 20-seconds, or 6/11, which is less than 1, so it converges. We're good. All right, 3 more, and then I'll make the FRQ video separate. So determine whether that series converges absolutely, conditionally, or it diverges. So the absolute convergence depends on, like if I take the absolute value of the sequence terms, all the negative terms would go away, and it's all just adding. That usually works for alternating series. That's the only time we look for absolute and conditional convergence. So this thing must alternate. Let's see why it alternates. So if I plugged in 1, that's the first counting number down here. So it'd be sine of 2 minus 1, which is 1 pi over 2. And what's sine of pi over 2? Sine is the y value. So sine of pi over 2 is 1. Then I plug in 2. 2 times 2 is 4, minus 1 is 3. So sine of 3 pi over 2. So you got like original down here. Sine there would be negative 1. And then I plug in 3. 6 minus 5 pi over 2. Sine of 5 pi over 2. That's back to that reference angle. So positive 1. That's the alternating part. So really this is just an alternating series. And if I took away that alternating part, it would just look like 1 over n. And by now, hopefully we know that this is a harmonic series that diverges. So if I take away the alternating part, it diverges, which means it does not converge absolutely. It converges conditionally, that condition being that it alternates, because we know alternating series converge. So this answer would be converges conditionally. It's an alternating harmonic. Determine the convergence of this P series. Oh, that's easy. Okay, I said that kind of, like, don't feel bad if you didn't see that right away. I looked at this earlier. I looked at this the other day. This would be 1 over n to the positive pi. And a P series is if your counter is the base and your P is the exponent. If that P number is bigger than 1, it converges. All right, last one. The n-term test can be used to determine the divergence for which of the following? Well, the limit has to be 0, right? Or can't be 0. This limit of just the sequence, that limit is 0, so I cannot use the divergent or the n-term test. Okay, this one is alternating, so I would look at the alternating series test. But even if I did, I'd look at just this. The limit of these terms of the sequence is 1/4. If I bring that alternating in, the alternating series, the limit goes back and forth to 1/4, negative 1/4, 1/4, negative 1/4. So that limit is not 0. The limit does not exist. So I could use it for number 2. The limit of, okay, this one, I would kind of square this part out. So the biggest term would be n squared, blah, 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 times another n. So it's n cubed on top over 3n cubed on the bottom. So that limit would be 1/3. So I could apply the n-term test there. So I could only do it for those two. The interim test only works for divergence if the limit is not 0. So it's B. All right, hopefully this helped. I'll do the other video is going to be the FRQ. Hopefully that question up here, I can think of an answer and tell you before I get to class. The alternating series, I feel like even though it like increases at first, as long as it decreases forever, kind of like the integral test, it should be okay. And it does for every n other than 1. So that's not making me real happy. But if I just like cut it off and I said, okay, just from here, if that converges and I add one other number to it, it would still converge. So I'm pretty sure I'm comfortable with saying it's D. Hopefully you can think about it and come up with a conclusion also. But thanks for watching. If you have any questions, next time I see you in class, make sure you ask. Bye.